Certificates are pieces of data that the server exchange during the TLS handshake when the client tries to connect to that server to authenticate itself, to make sure that, hey, client, you're actually talking to the right guy. Okay? And why are we so paranoid about this? Why do we need a certificate? And the reason we need a certificate is because IP packets that we transmit passes by so many computers and routers, and we do not trust these computers and routers and gateways and proxies, right? Because people can just fiddle and change things. In the public internet, it's sufficient to only trust the server authentication. That's enough for us. But sometimes you want the client to actually also authenticate itself. In a microservices environment, for instance, where services talk into kind of a cloud native environment where it's not really trusted, if you think about it, right? Then how do I know that the service I talk to or is talking to me is actually the service that is talking to me? You need a mutual authentication. That's where mutual TLS comes into the picture, and I talked about that in the whole picture. But regardless, whether it's client-side certificate or server-side certificate, the certificate is really large. Why is it large if it's just containing the public key of the server and some sort of a signature, right? And the domain name is some strings, right? And the subject and email probably or something like that. That's because that's not really what we just sent in the TLS handshake. We sent something called a certificate chain. It's a whole chain of certificate. Because if you just create a certificate yourself and you send it to me, that's not enough to trust you because you signed your own certificate. That's called self-signed certificate. It's not really trusted. So we need someone who is trusted to sign your certificate, and that's called the certificate authority, which is nothing but just a normal certificate. Right? But that certificate authority is trusted by another party, right? And that party is also trusted by another party, another certificate authority. Up until we reach something called the root certificate. So until we reach this root certificate is a self-signed certificate that the private key of that certificate is tucked in, hidden somewhere. I believe it's with the INA authority, if I'm not mistaken. But basically, that is a trusted certificate, and it's literally installed in all of your computers. Global sign is a root certificate, for example, right? That's one example of a root certificate. And that's basically installed on your machine. And if you detect that root, then anything that comes from the root is essentially trusted. And that's how you validate that the server is who they say they are. And that chain is very large. And very large. It basically takes the most of the handshake, right? And as a result, of course, it takes time to transmit. And I want to talk about that portion in this episode of the Backend Engineering Show. And also mention the ongoing RFC. There is RFC 8879 that is titled TLS Certificate Compression. Because guess what? Today, we do not compress the certificate. We encrypt it with TLS 1.3 at least. I'm going to talk about that. But we do not compress it, so that it's very large. And it has a side effect as a result. If something is large, it takes time to transmit, performance suffer. How about we jump into it and discuss? Welcome to the Backend Engineering Show with your host, Hussein Nasser. And certificates are thick, really large. And the reason is, stems from the idea of you cannot really trust anything that you get from a remote party. Right? So we need a third party kind of a situation where we trust in order to trust that certificate. And this certificate itself, which contains the domain name, which is the subject, which contains the public key of the server. And then itself, it's signed by a certificate authority, and it's the certificate authority, let's encrypt Google services and DigiCert, is also signed by another certificate authority, right? Could be another certificate authority, or could be the root certificate authority, right? Could be just the root itself, the root certificate. This chain can get really large, right? And if you look in any handshake that you have today, you will see, if you used Wireshark or TCP dump, you will see that the certificate chain is around 6 kilobytes, 8 kilobytes, sometimes 10. The largest I saw was, I think, 10 kilobytes or maybe 11 kilobytes, right? Of course, there could be larger if you have a certificate authority that is signed by another certificate authority that is signed by another certificate authority, right? And also could get larger if you actually include the root certificate. Because let's think about it real quick here. Yeah? If you say that, hey, the server will include the full chain, that means validating the full chain from the client side should be sufficient. Correct? But that's actually not right. You cannot rely on the certificate full chain that the server sends back to you to actually authenticate the server. Why? Because if I'm a malicious server, I can create my own root certificate, self-signed, and I can then create my own shady certificate authority. That's called Hussein Shady. And then I can sign that certificate authority with that root certificate that I just wrote. And then I can create a certificate that says google.com, claiming to be google.com. Right? And I include all the Google information. And I claim, hey, I want to claim to be google.com. If I then intercepted someone going to Google and immediately responded, instead of actually sending the request to Google, I responded back to the person, because let's say I'm with the gateway, right? And I responded claiming to be Google. I just forged the IP. And I write back, say, hey, here's the TLS parameters, and here's actually Google certificate. Trust me, please. You are actually talking to Google. And I include the full beautiful chain that I actually talked about here, right? Which is google.com signed by Hussein Shady, signed by the root certificate that I just created. And if the client relies solely on that chain to authenticate, they will follow that chain and until they will reach the root, and they will find that the root is self-signed, and they will not do any additional checks. Says, oh, this root is good actually, because the root is self-signed and sounds like it's good, right? If the client just did that, that's absolutely pointless, because every single thing will be valid in this case. That's not enough. And in this particular case, the clients will trust that it's actually talking to Google, which is not. And then I can serve it another page that looks good like Google, but it's actually a phishing page, right? And I basically have the client. Very bad. Very, very, very bad. So what TLS clients actually never do this. They take your certificate, they go to the certificate authority, they go back up until they reach the root certificate. And in that root certificate, they actually validate it against their certificate store. That's called the certificate store. Is where basically all the certificates that are root and trusted are stored in your machine. That's basically what the operating system installed. So whatever is in that certificate store, it's trusted. Did you add it? Nope. Someone else did. You just have to trust them, you guys. And that's why wherever you buy the laptop and whoever installs the operating system for you really matters, right? You can't just, hey, I really trust the government of Kazakhstan to, pre-ship my operating system for me. I definitely do. You know, because I call out Kazakhstan because they actually did something like that before. They tried to install a root certificate on every single machine that entered their country, effectively, something like that. But because I check that root certificate against that store, only then, if that public key of this root certificate exists in my root, then it's actually enough, right, for me to check that. And that's when I actually validate and trust it. But here's the thing. If you really think about it, including the root certificate is not really required, right? Just the fact that if you tell me that your certificate authority, the final the final node, just if you tell me that who signed you, what public key signed you, which root signed you, just the public key, just an identifier, that's enough, because I'll use that identifier to look up my root, and based on that, I trust it. Okay? Including the root is optional based on the RFC, the TLS RFC. But from my, looking up and sniffing TLS handshake, I think it's almost always included. Like Google always included the root for some reason. Last time I checked, right? So that's an additional like 1.2 kilobyte or whatever, right? That including the thick root certificate, that the self-signed one. I mean, if you configure your own Nginx, can you control that? I would control, like definitely if I control my Nginx server or my HA proxy or some other server, I will not try to not include that root certificate, because it's just pointless, right? It's just an additional thing too. If I want to optimize the performance of my handshakes, I will not include it. But I don't believe every web server allow you to actually have that low level, tuning. If you are at that level, you're on your own almost, right? This is a very low level change you're doing. But regardless, including the root or not including the root, that's still a large payload. Why is it large? The reason it is large is because, you see, given an MTU of the internet, which is 1500, that's the agreed upon, 1500 bytes. That's the maximum transmission unit of the medium of the internet. Like the lowest common denominator is 1500. Even if you have like a router that supports a jumbo frame of 6000, 9000 bytes, you're still almost always gonna run into a router that supports 1500. That's the minimum, right? So we always say it's 1500 MTU. What does that mean? It means that the corresponding IP packets has 1500 minus its headers, which is around 20 bytes. So that's for 1480 bytes. And then take another 20 bytes for TCP, because that's the common transport protocol, 20 bytes for the TCP header. That gives you 1460 bytes, maybe 66, because sometimes the IP header doesn't take the full 20 bytes. Yeah, takes less. So that's what you're playing with. You can only send a segment, a maximum segment size of 1460 byte. So if your certificate is 10 kilobytes, that means you have to send math. You have to send exactly 7 segments just to deliver the certificate from the server to the client. Okay? Of course, congestion control window plays big part here, right? We really don't want to send one segment number one and then wait for an acknowledgement from a client, and then they send the second segment and then wait for an acknowledgement from the client, and then send and 7 times. That will basically kill us. Okay? That's why the congestion window, we based on whatever I think you start, the initial window is 1 maximum segment size, which is like 460, and then it can increase exponentially with slow start. So, and every time you send and you receive an acknowledgement, this increases it. But because that the handshake is technically the start of the algorithm, the TLS handshake is technically the start of your connection establishment. It's actually the slowest because you did not give enough time for the connection to breathe, for the congestion window to actually expand, right? Because you just literally started with the handshake. You did the send, ack. Yeah, sure, we kind of increased that window a little bit larger, but then immediately we got the client hello, and then followed by the server hello. So TLS 1.2, funnily enough, has maybe better chances than TLS 1.3. TLS 1.3 suffers badly because of this, right? Why? Because TLS 1.3, it's a one round trip kind of a handshake where you send something and then you immediately respond and then you're done, right? It's just one round trip. In that round trip, you really want to deliver as much data fast. You don't really want to wait for an acknowledgement, right, from the client, a TCP layer transport acknowledgement, that is, I'm talking about, right? TLS 1.3 did not unlock its full potential yet, unfortunately, in my opinion. Again, I'm just theorizing here. Just because of that, if your certificate is really large, guess what? The client cannot finish the handshake unless it receives the full certificate.
Hey guys, Hussein from editing. As I was editing this portion related to the congestion window initial size, and I said that the initial size is 1. It used to be true that the initial congestion window size was 1 maximum segment size, which is 1400, 1500 bytes. But then in 2013, April, there was a new RFC, and guess who made that RFC? Google. RFC number 6928, increasing the TCP initial window to 10 maximum segment size. Oh yeah. So they thought about this years ago that they're going to run into this problem with TLS, right? Having large certificate. If they did not do that, right? So this is a server or a backend configuration where you can set what is the initial congestion window size. Setting it too high, of course, you risk that the client might not handle it. But they just set it too high. Right? That's why when I do the TLS 1.3 to Google, I see all the certificate segments get delivered without waiting for an acknowledgement. And that makes sense because their initial window is so high. So that might be a problem, but it's something to take into account for our backend application, because we have no idea who sets this contextual window. I never did. So probably whatever library, whatever proxy you're using should have the low level ability to change that congestion window. And I would set it to a higher value. 1 is too low, I think, especially if you're going to do a TLS, right? And then you're delivering this massive certificate. You don't want to send a certificate, like part of the certificate, and because your window is too small, you have to wait for the acknowledgement just so you can send the other segment, right? You want the window to be so large so that just like slam all the segments without waiting for an acknowledgement. This way, at least you can push all this data. This is just something I would like to add to the podcast. I think it's very useful because it bugged me while I was like, wait a minute, when I actually did that, I did not see the client actually acknowledging. Why? Is the server never waited for my acknowledgement? Why? Then, of course, a little bit Googling, and we found this RFC in 2013. We learn new things every day. Back to the podcast. So yeah, certificates are really large. And this RFC that I'm looking at right now, 8879, is called TLS Certificate Compression. And it is designed to include a new TLS extension that the client and the server will agree upon. And the client, of course, proposes first. And it will say, hey, server, here's a TLS handshake. Here's my client's hello. And here's my ALPN. Of course, the application layer protocol negotiation. I support HTTP 1 and 2. And I support also SNI, server name indication, maybe encrypted client hello, stuff like that. All this extension. And here's a new extension, TLS compression, right? TLS certificate compression. I want you to compress your certificate. Don't send me that bloated 10 kilobyte stuff. Right? Compress it for me. And now, if the server agreed on whatever compression algorithm it picks from the list, I believe gzip is one of them. Braille. Let's get the list actually, so I don't make shit up. gzip. It's called zlib. Sorry, zlib, Brotli, and Z is standard Z. So these are the three algorithms that they support so far to compress the algorithm. And when the server picks up an algorithm, compresses the certificate, it must of course include the length of the uncompressed message, the uncompressed, how large it is as uncompressed, and it also should include the algorithm that it used to compress. And when it does that, it then sends that compress. So it will compress it from 10 kilobyte, probably is going to go down to 1. So it fits nicely, because especially it's all text, like certificates all text, right? Certificates all text, so text, sorry. So compression is really, the ratio is really high, I think. And you can transfer that damn thing into a single segment. So it's really powerful if you think about it, right? If this gets implemented, I think it's going to be a huge, performance boost when it comes to establishing TLS handshakes. Now, let's explore how this will work in both TLS 1.2 and TLS 1.3. You see, in TLS 1.2, it takes 2 round trip to finish the whole thing. And in the first round trip, you get the certificate. And in the second round trip, you actually finish up the handshake and find out what symmetric key you're going to be using, both the client and the server. Right? So if that's the case, then in TLS 1.2, so the client does a client hello, says, hey server, here's a bunch of stuff. I support all these ciphers, and I support also this sets of key exchange algorithms, and here's anything, pick whatever you want, right? And the clients are also smart. If the clients support both TLS 1.3 and 1.2, it will actually include the TLS 1.3 stuff. So it will pick up a key exchange algorithm. Actually, it's called, I think, a security group that's called like X255, whatever stands for the standard, curve. Because, when you actually exchange parameters, there are so many parameters to pick from. So security people built up a group of secure parameters. As, hey, this is a group called X25505, whatever, I forgot what it stands for. And this is use the electric curve Diffie-Hellman with 256 bits of key size, and it's 128 bits of security, blah blah blah, right? So the client's actually smart enough to, if it supports both, it will include this information just in case the server actually supports 1.3. But let's say the server is only supporting 1.2. It will basically ignore the TLS 1.3 parts, and it will just pick up the pick up one of the trusted certificate from the client's list, and it will build up the key exchange. So the server will start the key exchange technically in TLS 1.2. It will build up its own private parameters, share the public parameters, and share the certificate. So technically we did not encrypt yet at that round trip. So the first round trip is just sharing, hey, we picked this, let's agree on this. So the client now have the public parts of the server and now can technically complete the handshake. So now the client will generate, based on the selected cipher, its own public and private parameters, and it will send back the that portion, that missing portion, to the server so it can complete the symmetric key. The reason we had the 2 round trip is because we did not let the client pick the cipher. That's the problem with 1.2, right? Leading to this extra round trip. And because of that, the certificate is technically not encrypted, it's transferred in plain text, right? And this finish up the round trip. So anyone sniffing TLS 1.2, you can see the plain text certificate in the wire. But you cannot change it, of course, because there is an integrity that protects the whole thing. Right? But that's another topic. In TLS 1.3, it's no. The client actually says, because the client supports both, let's say it's curl, and curl supports both, it will actually say, hey, here's a list of my software. By the way, here's my public part of the X255. Let me get the actual name. So TLS X25519. That's the group. That's the correct curve. And so this is what I saw, and these are the values that I picked. Let's communicate. And the server, if it knows TLS 1.3, it will just complete the handshake right there and then. 1 round trip, half a round trip even, right? So now the server have the full key. It completes it. So the symmetric key, it has it. So what the server does, it sends 2 portions. It sends its public parts of that key, because the client doesn't have it, remember? It only has its part. And the rest of the stuff, it just encrypts. The whole extension, the certificates are encrypted, the TLS extension. If you support any type of extension, pretty much the whole round trip, the TLS is encrypted, fully encrypted. The client cannot read it unless actually it finds the key, right? So the certificate is actually encrypted. So that's why if you sniff the TLS 1.3, you can't even see the certificate that is being sent back in TLS 1.3. It's all encrypted. But it's still encrypting a large thing will result in a large thing, right? It's still large, right? You can argue maybe it's larger. I don't know. Might be wrong there. I might be wrong there, actually. No. Encrypting something large, will it get larger? Yeah. I mean, it's a block cipher. Yeah. I don't think that it will be larger. I might be wrong there. I'm not a security expert. So the client will get that back. The certificate is absolutely useless here to the client. It cannot do anything with it. See what we added here with TLS 1.3. We actually added another step. We added an extra step where the certificate, in this case, has to be decrypted. So I have to finish the handshake first, find out the symmetric key, decrypt that certificate and everything else. Only then I can validate it. So we added a step, an extra step that didn't exist before. In TLS 1.2, it's plain text, so immediately verify, right? You can verify technically without completing the handshake, right? Because technically, completing the handshake is pointless if you fail the verification, right? So that's the thing. So think about the amount of work that you have to do if you have to encrypt in TLS 1.2. Once we implement this, right, we'll have to encrypt and we'll have to compress. Well, we have to compress first and then we have to encrypt. And the client will have to decrypt and then we have to decompress. And then it has to validate. Boy, that's a lot of work. And does that save us the transfer time? I think it does, right? Because remember, we're adding extra work at the client side here. And now I'm worried about other things. Right? A shady attacker that kind of can DDoS the client or the server, because the client can do the same thing. Huh? If your server supports client authentication, then I am a shady client. I can send this compression. I compress my data, then I encrypt it, and it's all garbage. I compress a movie. I send it to you, right? As hey, this is my certificate, right? And I also encrypt it, of course, with my key. But unless you support like a 0R2T in this case, right, where you actually encrypt it, then in this particular case, I can actually DDoS the server, because the server will spend all of its time encrypting and then decompressing, and then only after it decompresses that 3 gig movie, if I just, wait a minute, this is not even a certificate. What's going on? But I spent all the beautiful CPU time of the server. DDoS alert. Very bad stuff. So I think that's why people are aware of these things. So smart security people are thinking about all this stuff. Like, what are the ramifications of implementing something like that? That's the problem here, I think. Yeah. Another thing, like, we talked about this uncompressed length, right? You see, uncompressed length is a space, is an integer, or maybe 64-bit integer, that says, hey, this is the size of the uncompressed certificate. So if I fake a number, it says, hey, this is the compressed size is actually 1 kilobyte, but the actual uncompressed is 7 gigabyte. It's just a number. Based on the RFC, and I'm going to include it here, right? The client actually, the server, allocate memory first, 7 gig free memory, in order to put the uncompressed certificate in. So if I lied as an attacker, I can also run a buffer overflow attack on the server side, and I just make the server run out of memory. I don't know, so much stuff to think about here. I think it's a useful thing, but what do you guys think about this? Let me know in the comment section below. And if you're listening to the podcast, thank you so much. Appreciate you. You can tweet at me and HNASR, or email me h@husseinnasser.com for have these discussions. I love this stuff. Absolutely love. Guys, see you in the next one. You guys stay awesome. Goodbye.